What if I told you that there was a way to find the posterior probability distribution without defining a Bayesian model, without defining prior distributions, without defining the likelihood distributions, without using a sampler, and without drawing random inference samples?
Brilliant!
And what if I told you that this magic method works with complex models, like deep learning models? How's this possible? Well, let's find out. Welcome to Doco.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. We have a lot to cover today, so let's jump straight into VS Code. In the interest of time, I've prepared some Julia code in advance. You can find a copy of my code in my GitHub repository. There's a link to it in the description below. If you want to follow along, you can save a copy of this file in a tutorial folder on your computer. After you save the file, in VS Code, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square bracket. Activate the tutorial directory. Add the following packages: Flux, LaplaceRedux, and Plots. For today's tutorial, we will not be using the Turing.jl package. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. The Flux package is very careful about function names in the namespace, so you need to specify any of the Flux functions that you want to use in your session. For this tutorial, I'm using a random seed. Okay, now that we have our packages loaded, let's generate some random data. The LaplaceRedux.jl package comes with a convenient random data generator that we can use to create some toy data. This random data contains numbers that are of type float64, but the Flux.jl package expects data to be of type float32 and in certain formats. So let's do some type conversions and do a little reformatting. Now that this housekeeping is out of the way, let's visualize this random data to see what we're working with. The first thing we need to do is to split our data into features and classifications. This dataset contains two features, and the classifications are either a 0 or a 1. Okay, let's generate a plot of these features and classifications. So this data is clustered into 4 groups. The members in the upper left cluster and the lower right cluster are classified as zeros. And the members of the lower left cluster and the upper right cluster are classified as ones. While it may be trivial for a human to look at this plot and identify the classifications, it's actually quite difficult for a computer to perform this task. This is an example of a binary classification problem using data that is not linearly separable. In other words, you can't just draw a straight line or a continuous curve in order to split this data. There are several different methods that you can use to tackle this problem. One method is a machine learning approach. That's what we're going to do. We're going to use the Flux.jl package to solve this challenge as a supervised machine learning classification problem. The Flux.jl package is a machine learning package written in pure Julia that provides the user with a set of tools to build custom artificial neural network models. These models can be anything from simple perceptrons to complex deep learning models. If you're new to the Flux.jl package, or if it's been a while since you've used it, I have a couple of videos on the Flux package on this channel, episodes 508 and 509, that you may find useful. I provided links to both of these videos in the description below. This tutorial is not meant to be a Flux tutorial, but I will highlight some of the key concepts as we go through the code in this Flux section. For this tutorial, we're going to build a multi-layer perceptron, or MLP, which is a relatively simple deep learning model. Our MLP will have 3 layers: an input layer, a hidden layer, and an output layer. The input layer will have 2 nodes for the 2 features, and the output layer will have 1 node for the classification. The hidden layer will have 10 nodes. This is an arbitrary number of nodes, so feel free to experiment with different number of nodes in the hidden layer. The nodes within a layer are not connected, but the nodes between layers are connected to each other by edges. So the nodes between the input layer and the hidden layer are all connected, and the nodes between the hidden layer and the output layer are all connected. The parameters of this model are split into weights and biases. The weight is like the slope of a line, and the bias is like the y-intercept of a line, meaning that the weight impacts the direction and magnitude, and the bias adjusts for any noise. Each edge contains a weight, and each node in the hidden layer and each node in the output layer contains a bias. So there are a total of 41 parameters, 30 weights, and 11 biases. The nodes in the input layer do not have any parameters. The task for our machine learning model is to take the inputs, or features, and the outputs, or classifications, and build a model that fits this input-output data. This is done by quote-unquote learning the values of these 41 parameters. So when the model receives new feature inputs, the model can return the correct classification output. So going back to the code, we start by assigning values for the number of nodes per layer. Then we define our model by using a combination of the chain constructor and the dense constructor from the Flux.jl package. The chain constructor in Flux.jl has nothing to do with the MC chain in the Turing.jl package. In Flux, the chain constructor is connecting the neural network layers together. Sigmoid is the name of the activation function that we're using in this model. As soon as you define your model, Flux will assign random values for the weights and assign 0 values for the biases. You can view these parameters by using the params function in Flux, and you can index these parameters by using square brackets. Click on the Julia logo icon and click on the table icon for the variable named PS1. These are the initial values for the weights that are attached to the edges connecting the nodes from the input layer to the nodes in the hidden layer. There are 2 nodes in the input layer, which is why this table has 2 columns. And there are 10 nodes in the hidden layer, which is why this table has 10 rows. Input node 1 is connected to all 10 hidden nodes, and input node 2 is also connected to all 10 hidden nodes, for a total of 20 weight parameters between the input layer and the hidden layer. Now click on the table icon for the variable named PS2. These are the initial values for the bias for the 10 nodes in the hidden layer, for a total of 10 bias parameters. Flux initializes the bias values at 0. Now click on the table icon for the variable named PS3. These are the initial values for the weights that are attached to the edges connecting the nodes from the hidden layer to the node in the output layer. There are 10 nodes in the hidden layer, which is why this table has 10 columns. But there's only 1 node in the output layer, which is why this table only has 1 row. The 10 nodes in the hidden layer are all connected to that 1 output node, for a total of 10 weight parameters between the hidden layer and the output layer. Now click on the table icon for the variable named PS4. This is the initial value for the bias in the 1 node in the output layer, for a total of 1 bias parameter. Again, Flux initializes the bias value at 0. So these are the 41 parameter values that our model will try to learn on its own. The way a machine learning model quote-unquote learns is by trying to minimize a loss function. There are many different loss functions that you can select. For this tutorial, we're using a loss function called logit binary cross entropy. The average loss function will be used to keep track of our model's learning progress as it attempts to minimize the loss function. Next, we need to set up some variables that our model will need for training. Training is used for supervised machine learning, meaning that the way our model quote-unquote learns is by us quote-unquote teaching it by feeding in both the inputs and the correct outputs. Our model will ingest the input data and then attempt to find the parameter values that will result in the correct outputs. The learning rate is the pace in which the model will learn. Setting this value is something of an art. If this rate is too fast, then the model may not fully learn the data. If this rate is too slow, then the model may take too long to converge on a solution. There are many different optimizers that you can use with your machine learning model. For this tutorial, we're using the ADAM optimizer, whose name is derived from adaptive moment estimation. ADAM is a commonly used optimizer in machine learning since it uses momentum, which often results in a faster convergence on a solution. Each attempt to fine-tune the parameters is called an epoch. Setting the number of epochs is also something of an art. If the number of epochs is too small, then the model may underfit the data. If the number of epochs is too large, then the model may overfit the data. Okay, we're now ready to train our model. We'll do that by using a for loop based on the number of epochs. In the REPL, you can scroll to see a history of the learning progress. As the number of epochs increases, you should see the training loss improving, which is a measure of how well the model is learning. So, what just happened? Well, the model ingested the data and fine-tuned the 41 parameters to match the data. Click on the Julia logo icon and click on the table icon for the variable named PS1. You probably don't recall the initial values for these parameters, but all of these parameter values have been updated. Click on the table icon for the variable named PS2. Recall that the initial values for the bias parameters were all zeros. But after training, none of these bias parameters are zero anymore. The same goes for PS3 and PS4. Now that we have updated parameters, we can use this model to make predictions. Unfortunately, in its current form, this model doesn't return normalized values. What we really need are output values that are between 0 and 1, so we can use them to predict classifications. We can do that by writing a normalizing function. After normalizing the data, the output is now between 0 and 1. Okay, let's test 3 points. The first point will have a feature 1 value of -4 and a feature 2 value of +4. The second point will have a feature 1 value of 0 and a feature 2 value of 0. And the third point will have a feature 1 value of +3 and a feature 2 value of +2. Let's take a look at where these test points are located in the feature space. Now let's see how our model classifies these points. You can see the predictions in the REPL. So our model is predicting that the first point is probably class 0, and predicting that the third point is probably class 1. But for the second point, it's not sure, since the prediction is close to 50%. Let's take another look at the plot with these predictions. So these predictions are pretty good. The great thing about a machine learning model is that it can learn to do this on its own with a little supervision. So what's the problem? The problem is that these predictions are too confident. There's no degree of uncertainty about these predictions. Conceptually, this machine learning solution is like finding a linear regression line using the ordinary least squares method. Ideally, we would like some sort of probability distribution around these predictions, which quantify our uncertainty. A pure machine learning approach will not provide you with this information. But a machine learning approach combined with a Bayesian approach will provide you with this information. There are several different ways that you can add a Bayesian approach to this machine learning solution. In fact, the Turing.jl documentation includes a tutorial called Bayesian Neural Networks that shows you how to do just that by using the Turing.jl package. But an alternate approach is using something called Laplace's approximation, which will give you a similar result, but doing it in a very different way. That's what we're going to do. We're going to add a Bayesian approach to our machine learning model by using Laplace's approximation, which is made possible in Julia thanks to a package called LaplaceRedux.jl. Laplace's approximation, or the Laplace approximation, is an analytical way of estimating the posterior probability distribution. It's named after the French polymath Pierre-Simon Laplace, who invented Bayesian statistics. Unlike the Markov chain Monte Carlo approach, with the Laplace approximation, there is no need to set up a Bayesian model by defining the priors and the likelihood, and then drawing random samples from that model. Rather than using inference, Laplace's approximation jumps straight into estimating the posterior probability distribution. In Julia, you can take advantage of the Laplace approximation by using a package called LaplaceRedux.jl. LaplaceRedux.jl was created by Patrick Altmaier, who introduced his package at last year's JuliaCon 2022. Some of the motivations for using the Laplace approximation is that it works on some complex models. It doesn't require a lot of code, and it's very fast. So in the case of deep learning, trying to combine a deep learning model with a Bayesian model may take a lot of lines of code and may take a lot of computing power if you're using a more conventional approach. But combining deep learning with a Laplace approximation can be a more efficient alternative. When using the LaplaceRedux.jl package, the first thing you need to do is to use the Laplace constructor along with your machine learning model. And then you use the fitBang function to fit the Laplace approximation estimator to your data. And that's it. Notice that we didn't create a Bayesian model. We didn't define priors. We didn't define a likelihood. We didn't pick a sampler. We didn't draw any random samples. Bruh. Now before we get to the results, there's an interesting step that we've never seen before. With the Laplace approximation, it's possible to optimize the estimate by updating the prior beliefs after coming up with the approximation to the posterior distribution. In the LaplaceRedux.jl package, you can do that by using the optimize_prior bang function. It's difficult to describe what just happened, but let's take a look at an updated plot, which will visualize the Laplace approximation. What you're looking at is a contour plot, or contour map, of the feature space. You need to imagine that you're looking down from outer space onto a three-dimensional topographical map that's been overlaid on top of a two-dimensional satellite image. The darker areas are the valleys, and the lighter areas are the hilltops. The valleys and the hilltops are connected by continuous smooth gradients. The quote-unquote altitude values on this contour plot are the probabilities for the two classifications in this feature space. So the dark valleys are home to members that are class 0, and the light hilltops are home to members that are class 1. Now, this isn't just a pretty picture. We can use this to make predictions as well. Let's try making predictions using the same 3 data points that we used before with our Flux model. With the LaplaceRedux.jl package, you can make predictions by using the predict function. You can see the predictions in the REPL. These predictions are similar to the predictions that we got when using the Flux model. But these Laplace Redux predictions are less certain and more nuanced. Going back to the contour plot, we can see the uncertainty surrounding these predictions. Depending on which direction you move from the test point, you will either be moving uphill or moving downhill. This contour plot quantifies our uncertainty, which we couldn't find by using a pure machine learning approach. This is pretty amazing, right? If you're impressed with the LaplaceRedux.jl package and you want to show your support to the developer, then please consider going to the GitHub page and leaving a star. Now, before I go, I would be remiss if I didn't include a discussion on some of the pros and cons with Laplace's approximation. Today, you saw some of the pros for using the Laplace approximation, namely that it's simple, it's fast, and it works with complex models. So what's the catch? The catch is that the Laplace approximation only works for normal distributions. So if the actual posterior distribution is some other shape, then the Laplace approximation will not work. Also, the Laplace approximation only works for unimodal distributions. So if the posterior distribution is a bimodal distribution, then the Laplace approximation will not work. In addition, the Laplace approximation is considered to be not as accurate as using the Markov chain Monte Carlo method. So those are some things to consider when contemplating the use of the Laplace approximation. With that said, when it does work, the results can be amazing. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!